All right, let's get this action on the road. So 5.1, we're talking about reaction rate. So far we've talked about reactions and how they occur, but not at the speed. So this is looking at how fast products are made, or conversely, how fast reactants are used. Sometimes the questions will focus on how much it's used, and sometimes we'll look on how much it's produced. Now, the ability to speed something up or slow it down is good. Sometimes we want it faster, as in like an explosion. Sometimes we want it slower, as in something like when you're having pharmaceuticals that you're taking, you want them to last a long time. So this is why it's a main focus of deeper level chemistry. So you're used to rates from things like physics, maybe, or math. How much quantity changes over a given period of time? So speed of a car, you have something like miles per hour, how many miles in a given hour. The rate we're going to be looking at is concentration, which is looked at when we have these brackets, and this is of an example of an iodine molecule, over a change in time. And I see that this rate is negative, which means I know it's a reactant because it's decreasing, which is only what reactants do in these types of reactions. So when we're trying to define a reaction, we want to look at the rate for the reaction, change in concentration. So just like I said, how fast reactants are used up will be negative. How fast products are used will be positive. So the idea is the negative goes for their, again, change in time, which is from 2 time points. And then that would be the change in the concentrations from 2 time points. So again, this is reflecting of a reactant. Positive would be part of a product. So sometimes we are given graphs to help us interpret what is going on with each of these. So in looking at this chemical equation, I see nitrogen dioxide is being a reactant, which is why the concentration is very high. And my two products, oxygen and nitrogen monoxide, are very low because they don't exist. Sometimes they might start at a concentration due to the fact that they are existing, but most of the times they'll start at 0. So we can see that the reaction rates are either the buildup of a product like O2 or nitrogen monoxide, or a decrease in one of the reactants. They're proportional stoichiometrically, so the idea is that for every 2 moles of this that's used, I'm going to produce 2 of this and 1 of that, which is why you can see that I'm producing twice the amount of moles, or the concentration of nitrogen monoxide, compared to oxygen. So the idea is that tangents of this will give us a slope, a relative change in concentration over time. So they're equal to the slope tangent at that point. Now, keep in mind that as the reaction progresses, the rate is dependent upon the concentration. It's never going to be constant until you're at the end, and essentially the slope is constant. So these, as you can see, kind of decelerate as we get closer to the end, and kind of are starting off very steep at the beginning. This all has to do with things we'll talk about later with reaction rates. So again, a little bit more quantitative, as sometimes you'll need to pull these things off of graphs and get an idea of what is the slope and product at the function of time. If we're looking at, in this case, hydrogen iodide, we can see that there's an increase in concentration over 40 seconds. So that should give us a slope, much like there's a decrease in hydrogen over 40 seconds. So this gives us some information we can do some things with and look at the reaction rate with stoichiometry. Now, in most reactions, the coefficients of the balanced equation are not all the same. So we can see that there's a 1 to 1 to 2 ratio for the production of hydrogen iodide. So when we're looking at the chemical equation, every 1 mole of hydrogen, we're going to need 2 moles, or we're going to produce 2 moles of hydrogen iodide. So the rates of decrease are going to be equal for hydrogen and iodine, but be twice as fast for hydrogen iodide. So the rate of change will be different for these different components. Now, to be consistent, the change is the concentration of each substance multiplied by 1 over the coefficient provided. So the coefficient of the chemical equation is going to be this kind of concept. This will relate to things that are, in these cases, reactants, because they're negative, to hypothetical products, which are seen as positive. Now, there's a difference between what's called average rate and instantaneous rate. So average rate is the concentration over any particular time period. If I go back, this thing's always stubborn. this would be similar to this rate here. So what is the average over time? It's a linear approximation. The wider the time scale, the more that's going to deviate. If we did, again, a linear approximation from 0 to 120, that's going to produce a straight line, which will be very different than the curve. So the idea is that it's a linear approximation, think of the tangent, and that the larger the time interval, the more it's going to deviate from the instantaneous. So the average is over a period of time. Instantaneous is exactly what it sounds like, a particular time. So instantaneous rate's the change at a particular time. And this is looking at the rate of the reaction. So you have the slope at one point, found by using that slope at that particular point. Really, it's the first derivative, but we're not doing calculus, so let's move on without it. So we have this reaction occurring, and if we're looking at hydrogen, we look at the instantaneous rate as follows. So it decreased by 0.28 molarity over 40 seconds. So because it's a reactant, it's negative, and it decreased over 40 seconds, so we have the rate. We can also use the hydrogen iodide concentration that over 40 seconds, it goes up 0.56 molarity. But remember, it's a 1 to 2 ratio based upon its coefficient being 2. So the rate of the reaction is the same for each. Remember, this is the rate of the reaction, not the rate that this builds, or I should say is used up, and not the rate that this is made, just the rate of the reaction. So there are some factors that affect reaction rates. The first one is very simplistic in the idea that it's the nature of the reactants. Sometimes it can be based on the physical condition they're in. Smaller molecules tend to react faster than larger ones due to the fact that they have simpler areas to where they can react to. Gases tend to react faster than liquids, which react faster than solids. A lot of this has to do with particle size. And keep in mind there are some, obviously, molecules or elements that are more reactive than others, based upon all their things from the periodic trends and ionization energies and so forth. Now, when we think of solids, powdered solids are more reactive than blocks, big chunks, more surface area for contact with other reactants. Reaction rates occur because of the fact you have these collisions occur. So if we can increase the number of collisions in a given time, we increase the reaction rate. Like I said, some things are more reactive than others based upon their atomic structures. Ions react faster than molecules because you don't need to have any bonds being broken. We think of a lattice structure forming. If they're already ions, all they have to do is come together and boom, they start reacting. So there's just bonds forming. It saves some of the time. You don't need some of those activation energy components already ready. Temperature increases reaction rate because you have more collisions. The faster the particles go, the more they have contact with each other, the more that they're going to possibly collide and have a correct orientation with enough activation energy. General chemist rule, for every 10 degrees rise in temperature, the speed of the reaction doubles. Doesn't always work, just an approximation. We can use this idea to help you understand, wow, this is going to have a big increase if we increased 40 degrees compared to 10. Now, there is a mathematical relationship, which we'll take a look at a little bit later. But we won't be doing any of the calculations. So when you see it, or if you have seen it, don't be too worried. Other factors are catalysts. These are species, chemical species. They can be elements, they can be compounds, they can be atoms, they can be all sorts of things. And what they do is they speed a reaction without it being consumed, which means in the end you have the exact same amount you have with it. There's positive catalysts, most common time used to speed up a reaction. Sometimes it's called negative catalysts, which we might remember from biology as inhibitors, things that slow things down or inhibit some reaction from occurring. Because sometimes our body wants to do things more productively, and sometimes we want to slow things down so it doesn't do it, like buildup of toxins in our body. So the catalysts, though, can work in a couple different ways. If they're homogeneous, they're present in the same phase, meaning both solids, both liquids, both gases. Heterogeneous, present in a different phase. So catalysts provide an alternate pathway with lower activation energy. So if we have this idea of what we react with and what we end with, there's idea that we always need to be putting energy in. And that energy provides an alternative pathway of lower energy. In this case, we're using a non-chemistry example of how to feed ourselves. Normally we just cook some food. However, we might have a pathway that never reaches that maximum energy like it would be to cook the food, even though it's a couple different energies in order to get there, like the energy to choose which restaurant, what to order, paying the delivery person. So those all have some idea when we're trying to think of how much energy that needs to be put in, but it lowers these. Other ways, reaction concentration. This is where we talked about having more collisions. If you have a larger concentration, you have more molecules that can interact. This increases the frequency of them colliding together. If that's happening, you're generally going to have more reactions present unless the activation energy is so much higher than what's around. Concentration of gases depends upon the partial pressure of gases. So if we have a higher pressure, there's a higher concentration, because higher pressure means lower volume, if you remember your gas laws. So therefore, if they're a smaller volume, they're going to be colliding more often. Concentrations of solutions compared to the molarity. So when we have a solution, higher molarity means more particles available in a given size in order to react and therefore have more of a reaction concentration. And that's it. Let me know what kind of questions you have, and I'll see you soon.